Welcome back, folks. In lesson 5.5, we're looking at behaviors of implicit relations. Now, we've spent a lot of times finding tangents to curves defined explicitly, as in y equals. Okay, what we're going to do with this lesson is apply a lot of those same techniques, a lot of those same concepts to implicit relations. So let's get going with that. So problem 1 says, consider the graph of this guy right here, x squared plus xy plus y squared equals 27. Okay, now this is an implicitly defined relationship. Remember, explicitly defined relations can be written in the form y equals. Okay, here with the different y's and the y's, I could not solve this for just y equals some expression, which is why I will say it's defined implicitly here. Then along with that, I have a picture of that curve, just to give you an idea of what kind of shape we're looking at here. And again, what we're going to look at is finding spots where this curve has horizontal tangent lines. Okay, in other words, the mins and maxes. Also vertical tangent lines, and then also solve for points that have specific slopes. Now with the picture here, obviously we could kind of eyeball what the answers to those questions are, but we're just going to use that to kind of show what we're finding. We're going to show you how to find these analytically, in other words, with no picture, no calculator. So let's go ahead and get going with that. So first thing we need to do if we want to talk about tangent lines is we need to find the derivative of our relationship. Okay, so part A, find the equation for dy over dx, derivative of y with respect to x. Okay, and what we're going to do for that is take our equation here, x squared plus, I'm going to flip the order, I'm going to write that as y squared first, plus xy with 27. And what I'm going to do is I'm going to take the derivative on both sides of this with respect to x. Okay, we'll think of that in terms of our derivative operator. And when I take the derivative with respect to x of a term with just x's in it, things happen normally. Okay, a derivative of x squared is just a 2x. Okay, plus, then when I do something with a y in it, I've got to use my chain rule. We'll say the derivative of y squared is 2y, and then dy over dx, okay, because we're finding the derivative with respect to x, not y. And then plus, we'll just keep on going with that. Here I've got xy. Now that is the same thing as x times y. In other words, I have to use my product rule. So I'll have an x times the derivative of y, which is dy over dx, okay, plus the y times the derivative of x, which is just a 1 we'll write for now, is equal to the derivative of 27, which is just a 0. All right, so step 1 for that is to find the derivative of both sides of this equation. And then the next thing to do is going to be to find dy over dx. So we want to isolate and write by itself this part of our equation. Okay, for that, remember, we will get all the stuff without dy and dx's to the other side of the equation. So as in, I'm going to subtract 2x on both sides. And I'll also subtract a y on both sides. And that'll leave me with 2y dy over dx plus an x dy over dx is equal to the negative 2x minus y here. All right, next thing I can do is I can factor this dy over dx out of these two terms on the left. I can write that as dy over dx times 2y plus an x is equal to negative 2x minus y. And then finally, to get the dy over dx by itself, we'll divide both sides by what we're multiplying it by, this 2y plus x. That's going to cancel here, leaving us with just the dy over dx on the left is equal to the fraction, we'll just say negative 2x minus y over 2y plus x. All right, so there's an equation for my derivative. Solve for dy over dx. Again, something we already know how to do, but okay, something we'll have to do to ask some questions about tangent lines for this problem here. All right, now that we have an equation for our derivative, now we can answer questions like this. Part B asks, write an equation for the horizontal tangents. Now, horizontal tangents are going to happen when we have dy over dx. Our derivative is equal to 0. Now, so in other words, that's going to happen when that derivative we just found, the negative 2x minus y over 2y plus x equals 0. And anytime I have a rational expression like this, 0 is going to happen when my numerator is equal to 0. Okay, so for horizontal tangents, all I'm looking at is that numerator. It's going to happen when negative 2x minus y is equal to 0. And as far as this goes, I can't get x equals a number, I can't get y equals a number, but what I can do is I can solve it for one of the two variables and then substitute it back in to solve for the other one. For this one, I want to avoid fractions, so let's go ahead and solve this guy for y. I'll add 2x to both sides. That'll give me that negative y is equal to 2x. And then I can just divide by negative 1 on both sides to get the y alone. And that'll give me y is equal to negative 2x. Okay, so the spots on this curve where I have a horizontal tangent line are going to be the solution to y equals negative 2x that fits in this equation, that makes this equation true. So what we can do next is we can rewrite our implicit equation. Instead of y's, though, we'll plug in this negative 2x. So we'll have an x squared plus x times my y, which is negative 2x. All right, plus y squared, which we can, again, replace with just a negative 2x here. It's starting to look a little ugly, but the idea here is now I have an equation with just x's in it, so I should be able to solve that for x and get x equals a number, and then substitute it back in here to get the y. All right, so what do we have? We've got an x squared. X times negative 2x will be a minus 2x squared. Okay, plus negative 2 squared is a 4x squared is equal to 27. All right, 1 minus 2 plus 4 will be 3x squared is equal to 27. And to get the x by itself, we'll just divide by 3, which will give me that x squared is equal to 9. And then take a square root, which leaves us with x is equal to a plus or minus 3. All right, so I'll have horizontal tangents at x equals 3 and negative 3. Let's go ahead and figure out what those y coordinates are now. I can say y is equal to, taking this expression that we saw for a minute ago, negative 2 times the x, we'll go with the 3, which will be a negative 6. All right, so as far as an equation of the tangent line, we can say we have y equals negative 6 at the point 3, negative 6. Okay, so that'll be one of my answers, one of my horizontal tangents here. As far as what we're going to ask for, we can either ask for that equation or the point it happens at. All right, and we'll also have y equals negative 2 times the other x, the negative 3, which is equal to a positive 6. Okay, so our other horizontal tangent would be y equals 6 at the point negative 3, positive 6. All right, flipping back to our picture of this curve, let's see if what we just found made sense. We said we had a horizontal tangent at negative 3, positive 6, which looks correct. Okay, and I could express that line, that tangent line, as just y equals 6. Remember, horizontal lines, we can just use y equals equations. And then we also have a horizontal tangent at 3 comma negative 6. And we can write that line as just a y equals negative 6. Okay, so there's my two horizontal tangents, and visually, hopefully those are making sense. All right, part C, we want to know an equation for the vertical tangents to our curve. Now, I'm going to have vertical tangents when dy over dx is undefined. Okay, so our vertical tangents will be when our derivative does not exist. In other words, when that derivative is undefined. So I want to know when my negative 2x minus y over 2y plus x is undefined. Which is going to happen when the denominator equals 0. Okay, remember, we can't divide by 0, so we're looking for zeros in the denominator. So similar to what we did with the looking for horizontal tangents, we'll just set our denominator equal to 0. Oops, not sure where the 4 came from there. Solve that for one of our two variables. Okay, again, I'm going to solve this one for the x because I don't want to deal with fractions. So we can minus 2y on both sides. That'll give us that x is equal to negative 2y. Okay, and just like we saw for the horizontal tangents by plugging our variable back into the original equation, we can do that here. This time I've got an expression for my x, so instead of x squared, I'll just go negative 2y squared. All right, plus a negative 2y for the x times y, plus a y squared equals 27. All right, we'll work out with some similar answers to what we had previously. Squaring things out, this is going to be a 4y squared. All right, minus a 2y squared plus y squared equals 27. So this time we'll have 3y squared is equal to 27. And same idea, divide both sides by 3. That'll give me y squared is equal to 9. Take a square root. And this time we end up with y is equal to plus or minus 3. All right, so those are my y coordinates. And now to get the x coordinates, I'll go back to that original equation I came up with. X is equal to negative 2 times the y value, which will be a 3. So in other words, negative 6. Okay, as far as an equation goes, then we have x is equal to negative 6 at the point. The x is negative 6, the y is 3. Okay, we're kind of plugging that in backwards. We're plugging the y in to get the x. Don't confuse that. So there's one of my answers. And the other one for our other y, we'd have x is equal to negative 2 times the negative 3, which will give us a positive 6. So we can write the equation x equals 6, all right, at the point 6 comma negative 3. Once again, we can throw those lines and those points on our curve here. We said there was a vertical tangent, okay, where our second derivative is undefined at negative 6, 3. Looks like we found that here. And we can write that equation as x equals negative 6. Okay, remember for vertical lines, I can't write y equals equations. We have to go through the x-axis and write x equals. And the same thing, we have another vertical tangent at 6, negative 3. And we could write that line as x equals positive 6. All right, so there's my vertical tangents. All right, last thing we're going to do with this same equation, part D, is find the coordinates of all points on the graph where the tangent line has a slope of -1. All right, so instead of looking for a 0 or something that's undefined, we could look for other specific slopes. Okay, so in other words, here we want to figure out where our same dy over dx, that -2x minus y over 2y plus x, is equal to -1. All right, for this, what we can do, just like we did with our horizontal tangent lines and vertical tangent lines, is let's solve this equation here for either x or y. First step we want to do is get rid of our fraction. So here we're thinking of our entire equation, not just the numerator or the denominator. So I'm going to multiply both sides of this by 2y plus x. That's going to cancel out my denominator, leaving me with a -2x minus y is equal to, we can distribute here, -2y minus x. And then what we'll do is get the x's on one side of the equation, the y's on the other. As well as keeping things positive, I could add 2x to both sides. That'll give me that -y is equal to -2y plus an x. And then I can add 2y to both sides, canceling here, which will give me just a y is equal to x. Okay, so our coordinates are going to satisfy the two equations y equals x, and then also our original implicitly defined equation. Okay, so what we'll do once again is we'll take our y equals x and substitute it in here. Now for this one I could substitute y for x or x for y, it really doesn't matter. Let's do in terms of all x's. So this would be an x squared, okay, plus x times y, which again is just equal to x. All right, plus y squared, which again is just the x, is equal to 27. All right, so what we'll have then is 1, 2, 3x squareds. And again, get the x by itself, divide both sides by 3. We end up with x squared is equal to a 9. Okay, getting a lot of the same numbers with this equation. Take a square root of both sides. That'll give me that x is equal to plus or minus 3 again. All right, since my x is just equal to y, my coordinates will be 3, 3, and -3, -3 will both have tangent lines with the slope of this -1 here. And then again, going back to my curve, if I go to the point 3, 3, and if I plot a line that goes down 1, right 1 through here for slope of -1, and same thing, up 1, left 1 through here. Yep, it looks like that's going to be our tangent line with just a really crooked line there. Try to do better with the next one. And then -3, -3, same thing. That's slightly better. Yep, we'll have those points with tangents of slope -1. All right. A lot going on there, but kind of doing the same thing over and over again, just with different slopes that we're solving for. Why don't you take a few minutes here and pause this video, see if you can work through problem 2. So again, you'll find the dy over dx equation. Okay, find the vertical tangents, horizontal tangents, and then also a specific slope tangent. Now, problem 2 works a little cleaner, single solution instead of multiple solutions. Again, take a few minutes, pause that, and then unpause it once you're done to check your work out.